Okay, so now we are good to go. All right, so this is, guys, this is section 2.6. So in this section 2.6, we're gonna graph rational functions. So rational functions and their graphs. So we know how to graph polynomials. So now we're gonna learn how to graph rational functions. But so the first thing, what would be what's the definition of a rational function? So so let's start with the definition of a rational function. So a rational function is just a a quotient of polynomials, right? So rational functions are functions or are quotient of rational functions are quotient of polynomials. Quotient of polynomials. Okay, so what do I mean by quotient of polynomials? So your function f is actually of the form p of x over q of x. So where p of x and q of x are polynomials. Right? So for example, examples. So let's say f of x equals to, let's say x squared minus x plus 1 over 3x cubed minus 2x squared plus 2. All right. So you see, this is a quotient. It's a fraction, right? This is obviously this is so this is a quotient, right? Okay, and in the top we have a polynomial. So this is the polynomial p of x, right? And in the denominator, that's the polynomial q of x. Okay, so it's p of x over q of x, where p and q are polynomials, right? Another example number 2. F of x equals to x minus 1 times x plus 2 over, let's say, x minus 3 times x minus 1, right? Or let's say x plus 1. All right, so this is, so the question is the numerator, is it a polynomial? Is the top of a polynomial? So is this function here in the top, is it a polynomial? Well, the answer is yes, because when you if you distribute, so this is this is, let's say, p of x, and the denominator, it's called denominator q of x. So I mean, if you take p of x and which is x minus 1 times x plus 2, I mean, if you distribute, x times x squared, x times 2, 2x, minus 1 times x, that's minus x, and minus 1 times 2, that's minus 2, right? So anyway, so when you distribute, you get a polynomial, right, of degree 2. So this is a polynomial of degree 2. Degree 2, right? And the same for q of x. So if you distribute q of x, so q of x, which is x minus 3 times x plus 1, right? So if you multiply, you get x squared, x times 1 plus x, minus 3 times x, that's minus 3x, and minus 3 times 1, that's negative 3, right? So again, this is also polynomial. This is also polynomial of degree 2, right? So polynomial of degree 2. So this function f of x is a rational function, right? Degree of polynomial of degree 2. So this f of x is a polynomial, right? So yeah, so that's what I mean by a rational function. So it's just a quotient of polynomials, right? Now, the next remark is about the domain of rational functions, right? So, domain of rational functions. So rational functions, we said it's a quotient of polynomials, right? So we have a quotient, and remember, guys, when you divide, you have a division, you have a quotient, then you have to make sure that the denominator is not 0, right? So remember, guys, so for the domain, so if you have f of x equal to p of x over q of x, right? A rational function. So then the domain of f of x is because it's a, again, it's a division, it's a fraction, it's a quotient. So you have to make sure that the denominator is not 0, right? So then the domain is, you have to exclude the values of x where the denominator is 0. So the domain of f of x is where q of x is not 0, right? So for example, examples. So let's say f of x is x squared plus 4x plus 6, all right, over x squared minus 3 of x plus 2. All right, so this is, of course, this is a rational function, right? And so this is a rational function. It's a quotient of polynomials, right? So it's a rational function. Again, because it's a quotient of polynomials. So now, if you want to find the domain of f of x, so domain of f of x, so we have to solve. So then you have to solve denominator equal to 0, right? You have to solve the denominator equal to 0, right? Again, because it's a division, so make sure that the bottom is not 0, right? So solve the denominator equal to 0, so we have to solve x squared minus 3x plus 2 equal to 0. So this is just a quadratic equation, right? So then your x, it's minus b, so minus negative 3, plus or minus square root b squared, that will be 9, minus 4 times a times c, that's 8, over 2 times 1, right? So then x is positive 3 plus or minus square root of 9 minus 8, that would be 1. Square root of 1 is 1, of course. So it's plus or minus 1 over 2. So x is 3 plus 1 over 2. So that will be 4 over 2. That's equal to 2, right? Or x is 3 minus 1 over 2. And that will be 2 over 2. So that's equal to 1, right? So we got two solutions. The 2 and 1, right? So then the domain of f of x is any real number except the 2 and 1, right? So we have to exclude 2 and 1 from our number from the domain. So we have to exclude. So we exclude x equal to 2 and x equal to 1. So then the answer here, so the domain of f of x, so domain of f of x is negative infinity, 1 excluded, union with 1, 2 excluded, right? We have to exclude 1 and 2, right? And then 2 positive infinity. Right, so that's the domain of f of x. So it's any number except the 1 and 2, right? So that's how we find the domain of rational function, right? Because it's a fraction, it's a quotient, so make sure that the denominator is not 0. So we have to solve the denominator 0. Now another example, example number 2. So let's say f of x is equal to x plus 1 times x minus 3 over x minus 4 times x plus 5, right? So, I mean, this is also a rational function, right? Because, again, if you distribute the top, you're going to have a polynomial of degree 2. And the denominator, if you distribute the denominator, then you're going to have a polynomial of degree 2, right? But anyway, so you want to find, so this is a rational function, right? And then, so you want to find the domain. So the question is to find the domain of f of x. All right, so all you have to do is, again, solve. We have to solve the denominator equal to 0. So we have to solve the x minus 4 times x plus 5 equal to 0. Right. So this is kind of easy to solve because this is it's a product, right? This is a product equal to 0. Right here, this is a product equal to 0. So either either the x minus 4 is 0, or the x plus 5 is 0. So then x minus 4 is 0. So then x is positive 4. And x plus 5 is 0, so then x is negative 5. So we have to exclude 4 and negative 5 from the domain, right? So we have to exclude, so we have to exclude 4 and negative 5 from the domain. So then the answer, domain of f of x is so negative infinity, negative 5, union with negative 5, 4. Both of them excluded, of course, so we use parentheses, right? So union with 4 positive infinity, right? So that's for domain of a rational function. Is there any question, guys, about this rational function? So I hope you understand this notion of rational function. So it's just a quotient of polynomials, right? You have a polynomial in the top and a polynomial in the bottom, right? And then the domain would be, so you have would be the values of x where the denominator is not 0. So you have to exclude the values of x where the denominator is 0, right? Any question? All right. So now let's move to the graphs, right? So okay. So now so now the goal is to graph. Oops. So the goal now is to graph a rational So I'm going to show you how to graph rational functions in general, right? So graph rational functions in general. Right? So that's our goal today, okay? Or the goal of this section. So I'm going to start with two examples, okay? So we can see what happens. What will be the shape of a rational function? So let's first have a couple of examples. So example, right? So example one, I'm gonna take very simple, very basic rational function. So I'm gonna take f of x equal to 1 over x. Okay. So for my first question, is this a rational function? Well, yes, because, well, first it's a quotient, right? You see it's a, this is a quotient, right? You have a fraction, this is a quotient, right? Now, the top, so is the top a polynomial? Well, the top is just 1, right? Is 1 a polynomial? So what would be so this is a p of x, right? So what's the degree of the polynomial 1? What's the highest power of x for p of x equal to 1? Well, there's no x, right? And if there's no x, remember, guys, we said x to the power 0 is equal to 1, right? So this is, remember we said x to the power 0 is equal to 1, right? So this one here, it's actually x to the power 0. So this is like x to the power 0. So p of x is actually of degree 0 because the highest power of x is just 0. So p of x of degree 0, right? And the denominator, that's my q of x. So this is my q of x, right? And now what will be the degree of q of x? What's the highest power of x? Well, in the 1, yeah, right? So this is like x to the power 1 here. This is power 1, right? So q of x of degree 1. Right, so we have a quotient of a polynomial. So in the top you have a polynomial of degree 0, and in the denominator you have a polynomial of degree 1. Okay, so it's very simple, basic, a rational function, right? So f of x is a rational function because it's a quotient of polynomials, so it is a rational function. Okay, now I'm gonna try to sketch the graph of f of x, right? So now I'm gonna try to graph f of x. So I'm gonna make like a table values of f of x and see what happens. What will be the shape of the graph, right? So let's just make a table here with values. So here's, let's say, x. Here's my f of x. So my f of x is 1 over x, right? So let's say if you take x equal to 1, of course 1 over 1 would be 1. If x is 10, 1 over 10 is 0.1, right? If you take x, let's say 100, then 1 over 100, right? That's 0.01. If you take x, let's say 1000, that's 0.001, etc., right? So you can see if you take, of course, x 10,000, then this is 0.0001. So you see what's happening here, guys. So the values of x, so the values of x here, the values of x, so we have 1, 10, 100, 1000, 10,000, 1 million, etc. So the values of x are getting larger and larger, and actually they are approaching infinity, right? So here the x is getting larger and larger. Okay, and you can see it's actually, and so x is actually approaching infinity. So so you need to think of infinity, guys. So infinity is not, it's not a number, but you can think of infinity as a very, very large number, right? Like 1 billion or something, right? So again, infinity is not supposed to be a number. It's not a number, but you think of infinity as a very large number. Okay, so x is approaching infinity. Okay, so think of, so here, think of infinity as a very, very large number. All right, but again, formally it's not a number. Okay, it's not, infinity is not a number, right? But you think of it as a very, very large number. Now, what happens to the values of a function f? Well, so let's see here. Well, it's 1, then 0 0.1, 0 0.01, 0.001, etc. So the values of the function f are getting smaller and smaller, right? So values of f of x, values of f of x are getting smaller and smaller, right? And they are approaching which value? So you see here the values of f of x, they are getting close to 0, right? They are getting very, very small, so they are approaching 0. So f of x is approaching 0. Okay. It's actually it's gonna be it's never equal to 0, but it's gonna be as close as you want from 0. So this is really important. So the values of f of x there is gonna be, it's not 0. It's gonna be very, very close to 0, but it's never equal to 0, right? So but never, so so it's approaching 0, but never equal to 0. Equal. Okay. Okay, so the values of x is going to be as close as you want from 0, but never equal to 0. Right? So, okay, perfect. Well, of course, if you pick here, if you change the sign, if you put, if you put plus or minus here, plus or minus, plus or minus, plus or minus here, plus or minus, so we're going to get, of course, here plus or minus. All right, so the same remarks apply for negative values of x, right? I mean, if x is negative 10, obviously f of x would be negative 0.1, right? So the same remarks apply for the negative case. Okay. Anyway, so before the graph, so let me just fix some notation here. So when I say x is approaching infinity, so I'm gonna denote that by an arrow. So here I'm gonna fix some notation. Right? Okay, so instead of saying x, let's see here. So x. So when you say x approaching infinity, so I'm gonna denote that by x, an arrow, and then infinity. All right, so the arrow here means that x approaches infinity. So when I say x approaches infinity, it means that x is getting larger and larger, right? So x is as larger as you want, okay? So of course here, either positive or negative infinity, right? It doesn't matter, plus or minus infinity, Okay, so when you have an arrow, x arrow plus or minus infinity means that x is getting close to infinity, right? So it's approaching infinity, it's getting larger and larger, right? Well, you can have also the same thing. So now let's see. So this is when, so what we are saying here, so our conclusion here, so using this notation, so if you have, so let's say our function f of x is 1 over x, right? And what we are saying is that, again, if x approaches, you see here, x approaches infinity, or positive infinity, then the values of f of x, they approach 0, right? So let me write it down for you here. So the conclusion is that, so when x approaches positive infinity, f of x, the values of the function f that are getting very close to 0, they approach 0, so f of x approaches 0. Okay, and the same thing here, when x approaches negative infinity, right? If your x is negative, let's say negative 10, negative 100, negative 1000, etc., the values of f of x is gonna be, they're gonna be like negative 0.01, negative 0.001, etc., right? So they're getting close to 0. So when x approaches negative infinity, then the values of f of x, they're gonna be very close as you want from 0. Okay. So just one remark here. So when your f of x approaches 0, so you have your number line here. Here is 0, right? And you are saying your f of x is approaching 0. But if you have a number, right? There are two different ways to approach that number. You can approach the number from the left, or you can approach the number from the right, right? So like here, I can approach 0 from the left, right? So here I'm approaching 0 from the left. Okay. Or you can, of course, you can approach 0 from the right. 0 from the right. Okay. So to distinguish between the two cases, so when you approach 0 from the left, we're gonna put 0 minus. Okay. So here it's gonna be, here is the 0 minus. It means that you are approaching 0 from the left, and when you approach 0 from the right, we're gonna put 0 plus. Okay. So what I'm saying here, guys, is that like when x approaches positive infinity, f of x, of course, f of x is getting close to 0, but the values are positive, right? So you are approaching 0 from the right. So here, this is a 0 plus. Okay, and when x is negative, right? When x is approaching negative infinity, right? So when x approaches negative infinity, so we have like negative 1,000, negative 10,000, etc. The values of f of x, they're gonna be negative, right? They're getting close to 0, but they are negative. So it means that you're approaching 0 from the left, right? Because again, you see in your number line, if you are negative and you are approaching 0 you are approaching 0, so it means that you are approaching 0 from the left, right? Because you are negative. Okay. So here I'm gonna put 0 minus. This is 0 minus here. Okay. So again, this plus here means you're approaching 0 from the right, approaching 0 from the right. Okay, and this minus here, it means it's not the minus means you are approaching 0 from the left, approaching 0 from the left. Okay. Is there any question, guys? Does it make sense to you? The plus and minus here, 0 plus, 0 minus?
Yeah, it makes sense to me.
Okay, perfect. All right, so then, okay, so let's continue with the graphing our 1 over x. So we got this table of values. You know, we are saying if x getting approaching infinity, then values of f of x are approaching 0. Now, what about the values of f of x when x approaches 0? So let's make another table of values, so a different one. So here my x, here my f of x, okay, which is 1 over x. And now, instead of approaching infinity, I'm gonna approach 0. So the values of x, they're gonna approach 0. So let's say you start at 1, and then let's say you have 0.1, then you have 0.01, and then you have 0.001, etc. 0.0001. All right, so your x is approaching 0. X is never 0 because we cannot divide by 0, right? This is the thing, guys. We are approaching 0 because my function is 1 over x, right? So the denominator cannot be 0. We have to exclude 0 from the domain, right? X cannot be 0. So here, this is really important. So x cannot be 0 because 0 is not in the domain, right? Cannot be 0 because 0 is excluded from the domain, because 0 is excluded. That's where my denominator is 0, right? So it's excluded from the domain. However, you can take x as close as you want from 0, right? Never equal to 0, right? Never equal to 0, but as close as you want from 0. So now what happens to the values of f of x? So of course, 1 over 1 would be 1. 1 over 0.1, that would be 10. You know, 1 over 0.01, 100, 1,000, 1 over 0.0001, that's 10,000, right? So here, so what happens here to the values of f of x? So the x, my x, the values of x are approaching 0, okay? And actually they're approaching 0 from the left or from the right? Remember, I have my
This would be approaching it from the right?
Yes, absolutely. This is my number line. I mean, these values are positive, right? I mean, 0.1, 0. They're all positive, right? So we are on the positive side here, right? Positive side here, right? We're on the positive side. So we are getting close to 0, but we are positive, right? So the numbers are positive. So we are approaching 0 from the right. So this is a plus. My x is approaching 0 from the right. Okay, again, so this plus here means from the right, approaching 0 from the right. Okay. Now, okay, so now what happens to the values of f of x? Well, they are getting close to, well, I mean, 10, 100, 1,000, 10,000, etc. So they're getting larger and larger, right? So they are actually approaching infinity, right? So so f of x here is approaching positive infinity. Right? They're getting larger and larger. Okay. Now, of course, you can do the same thing with the negative. Negative values of x. So instead of 1, 0.1, 0.01, etc., you can have negative. Negative 1, negative 0.1, negative 0.01, negative 0.001, negative wherever, right? So you can do the same thing with negative, right? And so then the conclusion, of course, the values of the function f, they're going to be also negative, right? If x is negative, f of x is going to be also negative, right? So then the conclusion is that as x approaches, so when x approaches 0 plus, f of x, the values of the function f, they are approaching infinity, okay? And when x approaches 0 from the left, so this plus here, again, this plus here means we are approaching 0 from the right, approaching 0 from the right, okay? And the same when you approach 0 from the left, so when x approaches 0 from the left, so this is from the left, then f of x is going to approach negative infinity, right? All right. Okay. So now I'm going to use these informations to graph f of x. So now what's the shape of the graph? Okay, so now, the graph. So I have my f of x equal to 1 over x. We said when x approaches positive infinity, f of x is going to approach 0 from the right. When x approaches negative infinity, f of x is going to approach 0 from the left. When x approach 0 from the right, f of x approaches positive infinity. And when x approaches 0 from the left, f of x is going to approach a negative infinity. Now, if you graph f of x, so then you have something which looks like the following. Okay, so this is my x-axis. Right. All right, so here's my positive infinity. This is my negative infinity. Here's my positive. And here in the bottom, of course, that's negative infinity, right? And then here's my 0. Let's say here's 1, negative 1, 1, negative 1, etc. Anyway, so we said when x approaches positive infinity, so my x is in here, right? Then f of x, the image, the output f of x is close to 0, right? So then so I'm going to have my output very close to 0. So the 0 here, the output is close to 0. So it's going to be very close to the x-axis. So let's say positive infinity. So my graph is going to be very close to 0. It's never 0, but it's going to be very close to 0, right? You see here the output. So my x is at positive infinity, right? My x, here's my x, right? This is my x. It's at positive infinity, but the output is very close. You see it's very close. It's very close to 0, right? The output is very close to 0. Now, when x is close to negative infinity, my f of x is close to 0, so 0 minus. So it's a negative side. So then my graph is gonna be right here. So I'm gonna be very close to 0. So you see here my output. It's close to 0, right? The negative side of 0, right? And then now when x is approaching 0 from the right. So I'm approaching 0 from the right here, right? The graph f of x is going to be very close to positive infinity. So the output is going to be very close to positive infinity. Right, so you see here's my x is in here, right? It's very close to 0 from the right, and the output, it's actually you see the output here, it's very close to positive infinity. And the same when you approach x from 0 from the left. So you are on the left side of 0, so then your x, the output would be very close to negative infinity. So the image here is going to be very close to negative infinity. So so then the graph is going to be right here. Okay. So that's the f of x equal to 1 over x. Again, guys, because you see the zero is not in the domain, right? So there is 0 has no image, right? Because 0 is not in the domain. It's excluded, right? It's 1 over x, so x cannot be 0. So 0 is not in the domain, which means that 0 has no image. There's no output when x is 0, right? Okay. And so here you see this the graph of f of x, it's getting very close to the y-axis, but it's gonna never touch the y-axis, right? Because if it touches the y-axis, it means that 0 would have an image, right? But 0 is not in the domain, so 0 has no image, right? There's no output when x is 0. So you see here the graph of f of x, it's gonna be very, very close to the y-axis. This is your y-axis, right? Here's y-axis. So it's gonna be very, very close to the y-axis, but it's gonna never touch the y-axis, right? The same here in the bottom. Here in the bottom, it's the same thing. So here's your y-axis. The graph of f of x is gonna be very, very close, as close as you want from the y-axis, but it would never touch the y-axis, right? Because if it touches the y-axis, it means that 0 is in the domain. If it touches the y-axis, it means that 0 would have an image, right? But 0 is not in the domain. It's excluded from the domain. So 0 has no image, right? So you see here in the bottom here, this graph here, it's getting very, very close to the y-axis, but actually it will never touch the y-axis, right? Because 0 is not in the domain, okay? And the same thing here. When x is at positive infinity, so you see this part of the graph here. So we are very close to the x-axis. Here's your x-axis, right? So when x is approaching positive infinity, when x is very, very large, the values of the function f, they are getting very, very close to 0. So they're getting very close to the x-axis, but it's never 0, right? The values of f of x, it's never equal to 0. So here the same thing. So here's your x-axis. The graph of f of x is gonna be getting closer and closer to the x-axis, but it would never touch the x-axis, right? Because f of x cannot be equal to 0, right? This f of x here, it cannot be equal to 0. Right. The same thing here on at negative infinity. So here's your graph, right? It's getting very, very close to the x-axis because the values of the function f, they're close to 0, right? Very, very close to 0, but it's never equal to 0. So it won't touch the x-axis, okay? So you see here, so what I'm saying is, you see here, So it never, so the graph of f of x never touches the x-axis, but it can be as close as you want from the x-axis, okay? But it can be as close as you want okay, from the as close as you want from the x-axis. Okay. So yeah, same thing applies here, right? When x is positive infinity, same thing here. It never touched the you know the y-axis. Here, same, never touch the y-axis. It's getting as close as you want from the y-axis, but it never touched the y-axis. All right. Is there any question, guys?
Not right now. I think it's just probably show like a different example, maybe.
Yeah, I'm gonna do another example, sure. Yeah, so this is just the first example, of course. Yeah, so okay, let's have another example. Okay. Well, before the next example, let me introduce some terminology here. So okay, so definition. So when you are in the situation where, like, so here's an examples. So let's say before the definition, let's say, remark, I guess, remark. So when we are in the situation where we are getting very close to the, so let's see here. So we are in this situation where the graph, you see this graph here, it's getting very close. The graph is very close. The graph of f of x getting very close as you want from the y-axis, as close as you want from the y-axis, let's say, from the y-axis, but it never touches. Okay, so in this situation, we say that we call the y-axis a vertical asymptote. So we are in the situation where the graph is very close to the y-axis, but it never touched the y-axis, right? So then in this situation, we say that the y-axis, we call the y-axis a vertical asymptote. So the y-axis is called a vertical asymptote. Okay, so when I say a vertical asymptote, I mean a vertical line, right? So when I say a vertical asymptote, it means a vertical line. So it's a vertical line, right? And so your graph is getting as close as you want from that vertical line, but it never touched the line, right? So so that's actually definition. So let me just write down definition for the vertical asymptote. So definition. So the line, okay, so the line x equal to a. Okay, so the line x equal to a, that's like for the y-axis, what's the equation of the y-axis? So all the points on the y-axis have x equal to 0. So the equation of the y-axis is actually x equal to 0. Okay, so x equal to 0. So when I say x equal to a, line x equal to a, that's a vertical line. Okay, that's a vertical line. So vertical lines, the equation of vertical lines are always of the form x equal to a number, right? So for example, y-axis, that's x equal to 0 because all the points, if you take any point on the y-axis, the x coordinate is 0, right? So vertical lines, the equations of vertical lines are of the form x equal to a number, right? So the line x equal to 8, so that's a vertical line. That's a vertical line. So the line x equal to a is a vertical asymptote. Is a vertical asymptote of f of x if if f of x approaches positive or negative infinity as x approaches a from the left or from the right. Okay. So what I'm saying, guys, is that so you have your examples. So you have a graph. So let's say, and here's my x equal to a. This is the line x equal to a. A is here. Okay, some number a. All right. So my x is approaching a. So this is, of course, this is the x-axis, right? So my x is approaching a either from the left. So your x is here, or x approaching a from the right. So your x is here, right? So this is when x approaches a from the left, and here, that's when x approaches a from the right. Okay. Now, as x approaches a from the left or from the right, your function f is approaching infinity, right? So my infinity is supposed to be positive infinity, and here's my negative infinity, right? So the values of the function f are approaching positive infinity. Okay. So you see, guys, here's my x, and so the output, the image of x, when x is very close to a, let's say from the left, it's actually the output is approaching positive infinity. All right, or your x approaching a from the right, so like so your x is approaching a from the right, like here, right? So then the values of the function f, they're approaching positive infinity. So here's my f of x. So you see your x is in here, and the image output is actually approaching positive infinity. And again, guys, as I said, your graph, it's getting as close as you want from the line x equal to a. Again, this is my line, the green line, that's my x equal to a, right? This is my x equal to a. So the graph is getting very, very close, as you want from the green line, right? But it never touched the green line, right? So here the graph is getting very, very close to the green line, but never touched the green line, right? So that's what I call vertical asymptote.
But
And of course, yes.
the line on the left, the red line, that would usually be underneath, like in the negatives, right?
Yeah. Yeah,
Okay.
so yeah, and that's actually, so that's your graph, right? This is your, of course, that's the graph of f of x. Okay. And of course here, what will be the image? What will be f of a here? What's f of a? Any guess?
Would it be, I don't know, positive and negative? I definitely have no idea.
Well, f of a here is undefined because your graph, the red graph, the graph of f of x, it never touch the line x equal to a. It never touched the green line, right? If it doesn't touch the green line, it means that the image of a is undefined. So f of a actually is undefined.
So then would all graphs be undefined if they never
Yeah.
touch
So
the?
that's when we have a vertical asymptote. So when we have a vertical asymptote, so the graph is getting very, very close to the x equal to a, but it never touched the line x equal to a. So it means that a has no image. It's the image of a is undefined, right? Because usually, guys, if you have a graph, let's say I have a graph, all right, and here's my a. This is my a, and here's my graph. So how can we find the image of a? Well, we take the vertical line passing through A, right? And this point here would be the image, right? That would be f of A, right? This would be f of A, right? But here we are in this situation when we have a vertical asymptote. We said the graph, it never touch the vertical line passing through A, right? So if my graph, the graph here, sorry. So here, okay, so here, all right, so f of x, the graph of f of x, graph of f of x, and never touch the the vertical line x equal to a, the vertical line where x is equal to a, right? So if your graph it doesn't touch the vertical line x equal to a, then the image, the f of a is undefined, right? So you see here, I take this vertical line and it touch my graph at this point. So then this point would be the image of a, right, by the function f. But here, when we have a vertical asymptote, what we are saying is that my graph is getting as close as we want from the vertical line x equal to a, but it never touch. It's never equal to x equal to a. So it never touch the vertical line, right? Doesn't make sense to you guys? So that's what I mean by a vertical asymptote. Of course, here we are in the situation where the graph of f of x goes to positive infinity. Of course, you can have situations where the graph of f of x goes to negative infinity. So for example, you can have, oops. So let's say this is example 1, example 2. So again, I have this vertical asymptote x equal to a. This is my a, right? And then my graph. So my graph, it's gonna be as close as I want from my vertical line x equal to a, but I never touch the x equal to a, right? So here in this situation, right, the values of f of x that are getting close to negative infinity. So this is, of course, this is x equal to a, but here this is negative infinity, right? This is positive infinity. So what I'm saying is, if your x is here, right, my x is approaching a from the left, right? So my x approaching a from the left, all right? So what happens to the image? Well, the image, here's the image. Well, it's gonna be you see here, is going to be at negative infinity, right? Or if you approach A from the right, so this is X approaching A from the right, the image, the output, you see the output here is going to be close to approaching negative infinity, right? And again, we have the same thing. So the graph, it never touch the vertical line x equal to a, but it gets as close as we want from the x equal to a. So this is my, of course, this is my vertical asymptote. So this is my vertical asymptote. All right. Well, you can also have a situation where on one side the values of the function getting close to positive infinity, on the other side the values of the function getting close to negative infinity. So let's say we can have the following situation where, so let's say this is again x equal to a. So here's my x equal to a. This is my a. All right, so this is my x equal to a. So on one side, let's say the left side, my graph, it's, so again, this is, of course, this is positive infinity, and this is negative infinity. So on the left side, my graph is very, very, so it's close to, you know, my vertical asymptote, right? But it's at positive infinity. And on the right side, it's at negative infinity. Okay. And again, the idea, guys, is that your graph never touch the vertical asymptote. It gets as close as you want from the vertical asymptote, but it never touch the vertical asymptote because your f of a is undefined. Right? My f of a is undefined. Okay. And of course, here the values of the function f. So here you see the values of the function f is at positive infinity, and here the value of the function f is approaching negative infinity. Okay. Any question, guys? So that's for the vertical asymptote. All right. Now, of course, you have vertical asymptote. So like if we come back to our example 1 over x, right? In our example 1 over x, so you see here on on one side, this side here, left side of 0. You see here left side of 0. So your graph is getting very, very close to the y-axis, but it never touched the y-axis. So your y-axis is actually a vertical asymptote, right? So here you see right here, right? So the graph is very close to the y-axis, but it never touched the y-axis. The same here at the top, right? In the top here, but at positive infinity. So here we are at positive infinity. So you see here, so your graph is getting as close as you want from the y-axis, but never touch the y-axis, right? So that's why I call the y-axis a vertical asymptote. Okay. Now you can guess we're gonna have also horizontal asymptote. So you can see here, like my x-axis. You see here my x-axis is gonna be like a horizontal asymptote because the graph gets as close as I want from my x-axis, here and here, right? But it never touched the x-axis. So in that case, we're gonna have a horizontal asymptote. Anyway, so before the horizontal asymptote, let me show you first how to find, in general, how do we find a vertical asymptote? So the question now, Okay, so how can we find vertical asymptote? All right, so let me just come back to the case of 1 over x. So in 1 over x, guys, my vertical asymptote was the y-axis, right? We said here, so vertical asymptote, so y-axis is a vertical asymptote, right? And what's the equation of the y-axis? We said it's a vertical line, so it's x equal to 0, right? Because all the points on the y-axis, the x coordinate is 0, right? And so this x equal to 0, this vertical asymptote x equal to 0, that's exactly where the denominator is 0, right? The function is 1 over x, right? F of x is 1 over x, and x is equal to 0. That's exactly where my denominator is 0. So this is a general fact. So to find the vertical asymptote, we have to solve the denominator equal to 0. So how can we find vertical asymptote of rational functions? F of x equal to p of x over q of x. Well, all you have to do is to solve the bottom denominator q of x equal to 0. Okay, and then so the vertical asymptote, they're gonna be just the solutions of denominator equal to 0, right? So so for example, some examples. Let's say you want to find the vertical asymptote of so let's say just 2 examples. Let's say f of x is x fourth minus x cubed plus 3x squared minus 1 over, and let's say you have here x squared minus let's say 5x, okay, plus 4. Sorry. And so okay, that's the first example. So we want to find the oops. So we're gonna find the vertical asymptote, right? So so all you have to do solve. So this is my p of x, and the denominator is my q of x. So all you have to do is to solve the denominator q of x equal to 0. Denominator q of x equal to 0. So that's x squared minus 5x plus 4 equal to 0. And so that's, just apply quadratic formula, right? So that's minus -5, plus minus square root of b squared, that's 25, minus 4 times a times c, so minus 16. 25 minus 16 is 9. So this is actually square root of 9 over 2 times 1, 2 times 1, right? So your x is positive 5 plus or minus 3 over 2. And so and so your x is it's 8 over 2, which is 4, or it's 5 minus 3, it's 2 over 2, which is 1, right? So we got 2 solutions, 4 and 1, and so vertical asymptote, they will be x equal to 4 and x equal to 1. So then final answer my vertical asymptote. So my VA, vertical asymptote, are x equal to 4 and x equal to 1. Okay. So what does it mean that x equal to 4 and x equal to 1 are vertical asymptotes? So what does it mean for the graph? So in the graph, of course, I'm going to explain this later when we graph rational functions, when I'm going to show you the general steps to graph rational functions. But the idea here is that, so you're going to have, let's say this is x equal to 1 here. This is x equal to 4. So we're going to have a vertical asymptote. So remember, guys, vertical asymptote means vertical line. So I'm going to have a vertical line here at x equal to 1. This is my x equal to 1. And I'm going to have a vertical line at x equal to 4. And so my graph, so here I have positive infinity. Here I have negative infinity, right? And so the graph of f of x is going to be very close to x equal to 1, but never touch the x equal to 1, right? So it's going to be very close. It's going to be at positive or negative infinity, right? So we're going to be either in the top here or in the bottom here, okay? Or on the other side, you could have, so your f of x is going to be, again, on the other side, it's going to be very close to your vertical asymptote, right? But never touch the vertical asymptote. Or you could have something here in the bottom, right? At negative infinity. Or here at 4, same thing. Never touch the x equal to 4, but very, very close to x equal to 4, right? At positive infinity. So we are, the values, of course, the values of f of x are, approaching positive or negative infinity, right? So so then the graph on the other side, or you could have something here in the bottom. So we'll see later which side we're gonna, either your graph is gonna be in the top or in the bottom, right? But we're gonna be in one of these situations, right? So very close to x equal to 4, but never touch the x equal to 4, right? And of course, we're gonna use this to graph our rational functions, right? So, any question, guys? Again, this is the red graph. That's the graph of f of x. Okay. All right. So that's for example number 1. Let's take just another one more example. How to find the vertical asymptote. So example number 2. Example number 2. So let's say now, sorry, f of x is equal to, let's say, x cubed minus 3x squared plus 2 over x minus 2 times x plus 2. Okay. So for the vertical asymptote, guys, remember, just solve the bottom equal to 0. So we're going to find, again, the question is, of course, find vertical asymptote of f of x. So again, the bottom, that's my q of x. This is my q of x. All right, so we have to solve, to find the vertical asymptote, we have to solve denominator, q of x equal to 0. Right, and so here, q of x is just a product of two factors, x minus 2 times x plus 2 equal to 0. So you have a product equal to 0. So either the first factor is 0 or the second factor is 0, right? It's just it's a product equal to 0, right? This is a product here equal to 0, product, which is equal to 0. So either x minus 2 is 0, right? Or of course the x plus 2 is 0. So then of course, then x minus 2 is 0, x is positive 2, or x is negative 2. So we're going to have two vertical asymptotes. So answer here. So the vertical asymptote are x equal to 2, positive 2, and x equal to negative 2, right? And again, the idea is, so when you graph your function f, when you graph your function f, you're gonna have something which looks like, so here's my negative 2, here's my positive 2, here's my so my vertical asymptote at negative 2, my vertical asymptote at positive 2. All right, and I'm supposed to have positive infinity here in the top and negative infinity here in the bottom. All right, and again, the graph is going to be very, very close as I want from my vertical asymptote, but never touch the vertical asymptote, right? So we're gonna have something which looks like this here. Okay. Any question about the vertical asymptote, guys? All right, and remember, like here in this case, denominator is equal to 0. I got a positive 2 and negative 2, which means, again, we can, yeah, so thank you, Jesus. So it means that, you know, we have to, in the domain, we have to exclude the positive and negative 2, right? Remember how we find the domain of a rational function? Just solve the denominator 0. So here again, guys, f of 2 and f of negative 2 are undefined, right? This is, again, an emphasize on the fact that f of, you know, negative 2 is undefined, right? And f of positive 2 is also undefined because we have to exclude them from the domain, right? We have, because positive 2 and negative 2 are excluded from the domain, okay? Because positive or negative 2, both are excluded from the domain, right? That's where the bottom is 0. So they are excluded from the domain. And that's why my graph never touch, you know, the vertical asymptote. So excluded from the domain, right? Okay, so that's why my graph here, it won't touch, it cannot touch the, you know, it cannot touch the vertical asymptote because f of negative 2 is undefined, right? And the same for positive 2 here, right? So here at positive 2, here's my positive 2, and the graph is going to be as close as I want, but never touch the x equal to 2. All right, so before the examples, let's see, how much time do we have? Okay. Yeah, so as you can guess, after vertical asymptote, we also have a horizontal asymptote. Okay, it's the same idea. Your graph is going to be as close as you want from the horizontal asymptote, but never touch the horizontal asymptote, right? So after vertical asymptote, so now we have, of course, a horizontal asymptote. Okay, so now horizontal asymptote. Okay, so what's the definition? I'm going to start with the definition. I'm going to give you a couple of examples, and then yeah. So first definition. Right, so definition. So what's a horizontal asymptote? Well, it's called horizontal asymptote, so it's a horizontal line. So a horizontal asymptote. So the line y. So you see the difference between a vertical asymptote and horizontal asymptote. So vertical, it's a vertical asymptote. It's a vertical line. And what's the form of the equations of vertical lines? It's always like x equal to a number, right? Now, for horizontal lines, the equation of horizontal lines are of the form y equal to a number, right? So the line y equals to, let's say, L. So that's a horizontal line. Okay, so the line y equals to L is a horizontal asymptote. Horizontal asymptote if is a horizontal asymptote if f of x approaches L as x approaches positive or negative infinity. Okay. So okay, so here's the examples. Or before the examples, the idea. So the idea is the following. So let's say we have a graph, okay, and my y equals to a is a horizontal asymptote, right? So my y-axis, now I'm going to take this is my y-axis, right? This is my x-axis, is positive, negative, infinity, right? So I have my line y equals to L. So L is going to be on the y-axis. So here's my L, y equals to L. So the y equals to L is going to be this line here. So this is the line y equals to L, because if you take any point, guys, if you take any point on this line, like this point here, so what will be the y coordinate of this point? Well, it's L. Or if you take this point here, what will be the y coordinate? It's L, right? So all the points which lie on this blue line, the y coordinate has to be equal to L. So that's why the equation of the horizontal line is y equals to L, right? So yeah, so anyway, so that's my line y equals to L. So I'm going to just erase this here. Okay. And so what I'm saying is that, so it's a horizontal asymptote if the values of f of x approach L as x approaching, so you see here x approach positive and negative infinity. So my x is somewhere, so my x is, it's approaching positive infinity. Here's my x supposed to approach negative infinity, or it's supposed to approach positive infinity. So when my x is at negative or at positive infinity, the output, the image f of x, so f of x, you see f of x is supposed to approach L. So the image supposed to approach L. So here's my image output. So you see here, guys, the output is approaching L, right? It could be also on the other side. Also, it could be something which looks like this here too, right? So then my output, my x is in here at negative infinity, but the output, it's very close to L. Or if your x is approaching positive infinity, right? Your x is here at positive infinity, so then the values of the function, they're gonna be very close to L. So then the values of so then the values of function f, they're gonna be very close to L. So you see here, the output, it's gonna be, x is approaching positive infinity, the output is gonna be very close to L. Right? And the same idea, it never touch the blue line. So the graph it never touched the blue line, the horizontal asymptote, but it's going to be as close as you want from the blue line. So here, see here, it never touched the blue line, right? The graph will never touch the blue line. It's going to be very, very close as you want, but never equal to L, okay? So yeah, so that's what I call a horizontal asymptote. So when your x is always at positive. So you see my x is at positive here, at positive infinity, negative or positive infinity, right? And so then the values of the function, the values of the function, they are close to some number L, okay? Any question, guys? All right, so then let me show you how to find the horizontal asymptote in general, and then we're gonna have a couple of examples, all right? I guess next time we're gonna have more examples because I'm gonna show you how to use all these informations, you know, to graph rational functions. So yeah, so let me show you how to find. So now the question is, how do we find horizontal asymptote? So question. So how do we find horizontal asymptote? Well, the difference between horizontal and vertical asymptote, you see here in vertical asymptote, you could have like, in vertical asymptote, you could have like 2 vertical asymptotes, right? Or more than 2 vertical asymptotes, right? Or you could have also just one vertical asymptote, right? It depends where the denominator is 0, right? Now, for the horizontal asymptote, the good news is either you're gonna have only one horizontal asymptote or 2 horizontal asymptotes. So here, so how do we find them? Well, we're gonna use the following rule. Well, so let's say you have f of x, okay, equal to p of x over q of x, right? So p and q, of course, are polynomial. This is a rational function, right? This is a rational function. Okay, rational functions. Then there are 3 cases. Okay, so the first case is when the degree of the top. So there are 3 cases. So the first case is when, so if degree of p of x, if the highest power of p of x is larger than the degree of the bottom degree of q of x, then actually there is no horizontal asymptote. So no horizontal asymptote. Okay, so no horizontal asymptote. Okay, if the degree of the top, the highest power of p of x, is less of p of x is less than the degree of the bottom of q of x, all right, then y equal to 0. That's the x-axis. The x-axis is gonna be a horizontal asymptote, right? So then y equals to 0. So this is when I say y equal to 0, that's the x-axis. That's the x-axis. Okay. Then y is equal to 0 is the horizontal asymptote. Horizontal asymptote. Okay. Now the last case is the degree of the top is equal to the degree of the bottom. Last case, if degree of p of x is equal to the degree of q of x. Okay. So so you're gonna have like f of x. So let's say both are equal. The degree is equal, let's say, to n. So you're gonna have like x to the power n in the top. That is a subscript n here plus etc. And in the bottom, you're gonna have it's the degrees are equal. So it's also x to the power n, but a different leading coefficient here. So let's say here's b subscript n, right, plus etc. Okay, so this is supposed to be, you know, p of x over q of x. Okay, then the horizontal asymptote is going to be the ratio of the leading coefficient. So you take, okay, then the horizontal asymptote, horizontal asymptote is y equals to, so we're going to take the leading coefficient in the top over the leading coefficient in the bottom. So that's the a subscript n over the b subscript n. Okay. So that's the leading coefficients of p of x and q of x. Okay. So for example, examples. Let's say you want to find the horizontal asymptote. Okay, find the horizontal asymptote. Okay, so let's say you have first example. Let's say f of x is x fourth minus 3x cubed minus 2x plus 1 over x cubed minus 3x squared minus 2. All right. So of course, this is the top, that's my p of x, and the bottom is my q of x. So if you want to find the horizontal asymptote, all you have to do, guys, is to compare the degrees of p of x and q of x. So the degree of p of x, what's the highest power of p of x? It's 4, right? And the highest power of q of x is 3, right? So the degree of p is larger than the degree of q. So if the degree of the top is larger than the degree of the bottom, that will be the first case, right? That's if degree of p is larger than q, then there is no horizontal asymptote, right? So we are in the first case. So here the degree of the top of p of x is 4, and so it's larger than the degree of the bottom, the q of x, degree of q of x, which is 3, right? So we are in the first case. So we are case number 1. This is case number 1, right? Case number 1. So there's the answer here. So there's no horizontal asymptote. Okay, so no horizontal asymptote. Okay, now if the degree of the bottom is larger, So now let's say f of x is x squared minus 2x minus 1 over x, let's say x fifth minus 3x cubed minus 2, right? So degree of the top is 2. Degree of the bottom is 5. So degree of, so this is supposed to be, this is my p of x, this is my q of x. So degree of p is 2, that's less. So yeah, degree of p of x is 2, is less than degree of q of x at the bottom, right? Of q of x, which is 5. So we are in the case number 2. P, degree of p is less, right? So we said y equal to 0 is the horizontal asymptote, right? So in this case, y equal to 0. So this is case number 2. Case number 2. And so the answer, so y equal to 0 is the horizontal asymptote. Last case, last example, example number 3. Don't worry, guys. So next time, of course, we're gonna use all these informations. I'm gonna show you how to use this horizontal asymptote, vertical asymptote, to graph the rational function. So today it was just about, I had to introduce all these terminology, all these definitions. But next time we're gonna have the time to practice and to graph, the rational functions. But today it's just about introducing the horizontal, vertical asymptote, etc. But anyway, so the third case, let's say f of x is equal to x minus 1 times x plus 2 over x minus 3 times x minus 4, let's say. All right. Okay, guys. Question: what's the degree of the top here? What will be the degree of p of x? What's the degree of p of x? Any guess? What will be the degree of the top? No, actually, Carly. So that's the thing. So here you have to distribute. So because when you distribute, like you multiply x by x, you're gonna have x squared, right? And then of course here x times 2 is 2x, then minus x, right? So yeah, here the same in the bottom, minus 4x, so minus, yeah, that's like a kind of a trap here, but yes, so it's actually both are of degree 2, so they are equal, so the degrees are equal. So in this case here, degree of p is equal to the degree of q is equal to 2. So what we do in this case, when we have the same degree, so we have to take the ratio between the leading coefficient. So the leading coefficient here, this is 1 times x squared, and this is 1 times x squared, right? So then y equal to 1 over 1. Okay, that's my horizontal asymptote. Okay, is my horizontal asymptote. Of course, 1 over 1 is 1, right? So you take the ratio between the leading coefficient, right? So of course, if I had 2x squared here, that would be 2 here, right? Or if I had like 3 here in the top, so that would be 3 here in the top, right? So just take the ratio between the, so here, of course, it's just 1. So just take the ratio between the leading coefficients. So it's 1 here, in the, sorry. So it's 1 here in the top and 1 here in the bottom. So that's my horizontal asymptote. Okay, so this is 1 here and 1 here. Right? That's my horizontal asymptote. Okay, so we are done actually. vertical asymptote, horizontal asymptote. So next time we're gonna have everything we need to graph rational functions. So we know now how to, how to find the horizontal vertical asymptote. We know how to compute and find the horizontal and vertical asymptote. All right. So then next time we're gonna just we can start graphing rational functions. All right, guys, just 1 minute left. So I guess I will see you next Monday. All right. Thank you, everyone. And please let me know if you have any question about the homework, just email me, right? So thank you, everyone. Take care. See you next time.